Wolf said I sound silky. Silky but loud. I'll take loud silk.
Loud. He's super
Loud.
loud. Okay, I can adjust it, guys. I can adjust it.
Patience.
I got this. Look at how. Okay, keep talking now.
I wanted people to say I sound silky because no one ever describes my voice as silky.
No one has ever. Well, you have a few people that have now. So, is it better now?
Now I can
guys?
say. Now I can say. People say I have a silky voice.
That's better. Everybody, yes, Paul is loud compared to you. Well, is it better now? Everybody, I need everybody to.
Let's just both talk at the exact same time, and people can
just talk over each other.
Our voices, talk over it to make sure it's balanced and one isn't
have really important things to say.
Other.
Just
and
making sure
we can go on about
forever.
The silkiness because I'm actually really enjoying that.
Yeah,
all the compliments on my voice.
Exactly. Sound level, video, all good. Great.
We did it. All right. See you guys next week.
We're done.
That's what always gets me about TV shoots and film shoots is it is so mind-numbingly boring because they spend 98% of the time just adjusting everything. Camera, lights, setting. And then you just stand around staring off in the distance, not doing anything. And then they're ready and they're like, go. And then you do your thing and they're like, okay, we're done.
It's over.
It's over.
Yeah. See how quick we did that though? We did that super, super quick.
We're pros.
Maybe Sky is a tiny bit louder. Okay. Well, so
now we're just nitpicking.
I know. Now, how is that? Is that a little bit better?
And my volume will change as I get more or less excited about a particular topic.
Well, I noticed you're actually in a hotel room.
I'm totally in a hotel room.
I've never seen this before.
A hotel room?
You and
so
one.
It's this really cool thing where you rent, like it's like a mini house, like just a portion of a house, and you just rent it for, a few nights. It's that way you don't have to buy a house everywhere you go.
Gotcha.
Which like I can afford. My financial manager just gets so annoyed.
Yeah, I would imagine. I would imagine so. But, I bet you get a lot of bottles of, the mini bottles of conditioner, shampoo. I bet you have a large supply of those. You're never going to run out.
Yeah, because I don't use shampoo.
That's what I'm saying.
I know I bring them back and my niece turns them into slime.
Everybody, I'm sorry. I'm recovering from being sick. So when I laugh, it sounds really bad.
You sound like Gollum.
I know. My precious. I know. I do. I totally do. Chico says, I feel him. So actually, someone just asked a question. I was just showing people. Did you see that radio image of the center of the Milky Way?
Isn't that gorgeous?
It's beautiful.
I flagged it to talk about on Space Radio.
Yeah.
This week. I love that image. That is a stunning, stunning image.
Yeah, I had just gotten to the press releases because we've been not doing space because I've been sick and my brain does not like to
function.
Yeah, not when I'm sick. So, but that is super cool. Do you want to tell people a little bit about? Wow, a little bit about that.
A little bit of
it.
It's a radio image, isn't it? From a new array called Meerkat, which stands for something, but it's in South Africa, which has a lot of meerkats. And so I guess they named it after the animal and turned it into a backronym. And this is a radio telescope array, which is something that people have been doing in radio astronomy for a long time. And you're going to see more and more of this kind of instrument where it's not just one dish or one antenna. It's a whole bunch of dishes, a whole bunch of antennas, all arrayed together. And you can get incredibly high resolution images with this kind of array. You can just pin down to very, very, very small scales. And this image was almost like a test image of, they've been running it, they've been doing tests, they've been building this thing for a few years. They're pointing it at the center of the Milky Way galaxy as kind of a showpiece image to show the public that, Meerkat is online and fully functional and ready to do some awesome science.
Yeah, I mean, it's gorgeous. This is wallpaper material for your PC.
Yeah, all these colors, these are, of course, are not natural colors,
right?
Because this is a radio telescope. If you could see radio and you mapped radio intensity to a particular color, this is what you'd see.
Yeah, so it's a very low frequency wavelength, right?
Yeah, like car radio frequencies.
Yeah. Always hate no, but I don't have any preference for Mac or PC. Can you please link the article? I can, and all of this stuff will be linked also, guys, in the VOD description per usual, because that's what we do.
It's VOD.
It's the if people want to go back and watch this on things.
Video on demand.
That sounds
very
really
old dimes.
I have no idea, actually.
Vivacious Orangutan Dreams.
Yes.
Okay, that one.
Mm-hmm. Wouldn't you hear it if you listened to that radio, though? Kappa, but maybe not Kappa.
Yeah, you can. So radio waves, travel through the air, and then we can tune them in a particular way so that they contain information about sound, and we can reconvert those radio waves into sound. So yes, you can apply the exact same technique, point this at the center of the galaxy, and you would probably just hear
sounds like a good ASMR channel.
The greatest.
Yeah.
You're listening to Center of the Galaxy Radio. Now sit back and relax and
Perfect. Yep, that's great. I think we have a new idea, Dr. Paul.
You got the point. Yeah.
I think we have a way to make a lot of money.
Tons. I mean, tens of dollars.
Tens. So yeah, and that's I didn't even know they were working on something like that. And what does that
There are new radio arrays going up.
Good.
All over the place. And by all over the place, I mean deserts, because you want really, really, really quiet places. And you can't have radio interference from human radios and human communication. So you go to the deserts because nobody lives there. And you can set up exclusion zones where people aren't even allowed to bring cell phones or digital equipment on site, so you can keep things nice and quiet. There's this famous story from the I want to say Perkins Observatory, but I think that's wrong. It's an observatory in South Australia, just north of Melbourne, that for over the course of decades, it's a massive radio telescope. Every once in a while, they would get these little high frequency blips and bloops. Like once a year or something. It would just like boop, and it'd change frequencies and go away. And they gave a name to it. They called it peritons. It's some literature reference. And it was written about, studied, and just like, where are these things coming from? It wasn't tied to any astrophysical source. It was just really, really weird radio signal. And a grad student figured out the mystery eventually, that the culprit was the microwave in the visitor center. That every once in a while, someone would open the door without turning off the microwave, and a little bit of microwave radiation would leak out, and that was enough to trigger the telescope.
Wow.
And give it a little bloop.
So was there microwave usage restrictions after that? No more.
Yeah,
like
I'm sure they put up
popcorn?
a very polite sign.
Yeah.
That said, make sure or they just got new microwaves. I don't know. I don't know the postscript to that story.
Yeah. Someone says, Paul, when will the Event Horizons image of the center of the galaxy be finished?
Oh, who knows? It's supposed to be this fall. I have a feeling it's going to take longer. These this is a technique. This is a thing called Aperture Synthesis, where you take multiple instruments like an array, like the Event Horizon Telescope Array or this Meerkat Array, and you combine all the images and all the data from all the instruments. That is actually an incredibly tricky and I want to say not the most scientific process. There's a little bit more art than science into creating these kinds of images. And it's not an easy thing to get it right and to know that you've gotten it right. So I wouldn't be surprised if the Event Horizon Telescope images take longer than this fall to finish.
Yeah. Let's see. There's other people. I think there was another question. I just have to scroll up for it. So what other news have you... well, actually, no. I was talking about your hotel room. So are you doing something? Where you at? Why you places?
Oh no, I just renovated my bedroom, my office, make it look like a little cozier. Put in a bed. And
are you doing something with astronomy right now?
Yeah, I'm in DC actually, and I'm here for a few things this week. One, I'm filming with the Science Channel. Two, Wednesday, I'm headed up to New York just for the evening to speak at an event with a very cool modern dance company, a collaboration I'm part of.
Oh, right.
And then most of the week, I'm here for a conference from the Department of Energy. They put on they fund a graduate school fellowship called the Computational Science Graduate Fellowship. This is for computational scientists who use a computer a lot, and in any field of science or engineering. And it's a relatively prestigious award. There's only 15 to 25 fellows awarded every single year. And this award lasts for 4 years. It pays for your graduate school for those 5 years, gives you a big stipend, gives you opportunities to visit national labs and spend time there and come to an annual conference. I am, of course, an alumnus of the program. Mm-hmm. And they invited me to come give a keynote about science communication.
Awesome. So what are you going to be talking about for the keynote?
So I did my keynote this morning and I turned it into a conversation because I didn't really want to prepare 45 minutes of material. So instead, I just made a bunch of question prompts, like if there was one thing you could tell the world about your discipline or your field, what would that be? What do you hate about current state of science journalism? What are some benefits to science outreach? What are some pitfalls? What are some barriers that you think you might run into? Just kind of hosting this conversation with a room of 200 people.
Cool. That actually sounds really, really amazing.
It was a very fun.
Yeah.
I think the talk will end up online, and if it does, I'll share it with you.
Please do, because we'll love to watch that. So Graham asked, excluding dark matter and dark energy, what astronomical theory would you like to solve?
There are, where do you start?
I know.
There are so many things we don't understand about the universe, especially the early universe. We don't understand this process of inflation. Mm-hmm. We don't understand why there's more matter than antimatter. We don't understand the state of the earliest universe, like the raw physical state of the early universe. We don't understand how the first stars formed. We don't understand the relationship between giant black holes and galaxies. We don't understand how energy is transported in a galaxy efficiently. We don't understand, this list could just go on and on and on.
You can't pick one?
No, and I refuse.
I refuse.
Well, I refuse.
Well, there was that whole thing about the neutrino.
The sterile neutrino? Is this a new
oh my gosh
new neutrino?
Oh my gosh. This was the distant quasar. Wait, is that it?
The super high energy neutrino.
Yeah. So the Fermi traces the source of cosmic neutrino to monster black hole. Yeah.
That was cool. Yeah, and actually some colleagues over at Ohio State University were part of that collaboration, part of that paper. Very exciting result for them. Like, when I reported on that in Space Radio last week, and because the news broke that Thursday morning, and what I took away, what I really wanted to communicate to people is that we are using the Antarctic ice sheet itself as a physics experiment.
Go on.
This detection was done with the Ice Cube Neutrino Observatory, which is located at the South Pole. And uses what we learned when we're looking for neutrinos, which are very, very tiny, ghostly ninja particles that hardly ever interact with matter, is that sometimes they do, very, very rarely. One will just strike an atom. And when they do, it leads to a cascade of new particles and a flash of light. And if you have a really pure container of water, it's really easy to see those flashes of light. You get these lovely little blue flashes. And so neutrino detectors in the past that we've used to look at supernova or the sun have been giant tanks of water. And we wanted to go bigger, but we were starting to run into engineering limits because there's only so big of a bathtub you can build.
Right.
And we looked around and we realized that the Antarctic ice sheet itself is amazingly pure water ice. So they went to, this is a National Science Foundation facility located at the South Pole. They took 1 square kilometer of ice and sunk strings of detectors down into the ice itself. And just wait. They just wait. And every once in a while, a neutrino strikes the ice in the vicinity of the detectors. The detectors see the flash of light and they can reconstruct the energy of the neutrino, where the neutrino came from, all that good stuff. And it is the craziest, most mad scientist experiment I can think of in particle physics.
Yeah. So what did it? So we watched the whole conference that they had.
Nice.
And I have to admit, I was pretty sad with the delivery of this news because I feel like they didn't really tell you what was going on. No layman's terms, whatever.
Right.
And so I wanted you to talk about it because again, showing, why science communication is important. All they kept saying is like, oh, so what does this actually tell us? They had the Q&A at the end and they're like, so what is this? What is this?
Why are we here?
Why are we here?
In this press conference, in this stuffy room.
Right. And their answer was, there's so many things we don't understand about the universe.
Oh, it got really vague.
Yeah. And I was like, that's what you just say when you don't know how to actually put that in terms.
That's what I say to kindergartners.
Yeah. So can you tell people what this told us? And also, you told us what a neutrino is, but like, what does this mean for the future? Why is this so exciting?
Honestly, I don't know why this result got a press release. I don't know why it got a conference. It's really cool. It's the result itself isn't the most interesting part of this aspect. We saw a high energy neutrino and we were able to use other telescopes to pinpoint the origins of that high energy neutrino. And it came from a active galactic nuclei, an active galaxy that was flaring.
Yeah, like 3.7 billion light years away.
It's far away. It's far away. And it was undergoing a period of flaring where the black hole was consuming a lot of material at once, lots of crazy energetic, lots of energy available, kicked off some high energy particles, which created some very powerful neutrinos. And that's neat. But I think what the line they were trying to thread in the press conference and what this signifies is that this is going to be the first result of many results. What they were able to do was ice cube experiment, saw a high energy neutrino, told the world of astronomy, hey, everyone, we've got a high energy neutrino, and it came from that part of the sky. And very quickly, a bunch of other instruments were able to say, oh, okay, hold on, let me look at that part of the sky and see holy crap, there's lots of cool stuff happening. And that kind of synchronous, time-based, instant readiness astronomy with multiple wavelengths and multiple kinds of observations is where astronomy is going. That is the next big deal in astronomy, is something we call multi-messenger astronomy.
Yeah, and Uncle Bill just said, is the galactic flow an issue for IceCube's location, and will it still stay stable and functional long term?
Right. So this is one of the reasons they put it at the geographic South Pole, where they don't have to worry too much about flows of ice. I have talked with, I'm friends with some postdocs and faculty that work with IceCube, and they worry about every once in a while it does snow, and it's very, very rare because it's a desert down there.
Right.
But it does snow, and that changes the properties of the ice. It does very, very slowly change with time. And so they have to kind of retune the sensors to account for that and adjust their data analysis to account for that. But it changes slowly enough that it's basically constant.
Yeah. And I'm seeing right here. Well, then someone, random question, but it's okay. They can be random. They don't have to be on topic, guys. Someone says, how much does it cost to go to space?
How much does it cost? What is the current launch price for space? Is it $10,000 a pound or $10,000 a kilogram?
I'm not sure. You know, I just don't think I'm going to be taking a trip anytime soon. I mean, even within the U.S., it's looking a little rough right now.
Yeah. I think it's somewhere around ballparking $10,000 per kilogram.
Someone said $10,000 per pound. I need to go on a diet. It's a Virgin Galactic is saying a trip to space would cost you around $250,000. That's it. I would think it'd be in the millions.
Except Virgin Galactic might kill you.
Right, you might die. Maybe that's
you might die.
So that's why
I know
cost.
Elon's goal is to bring people to Mars for $250,000 per person, which is like the equivalent of buying a house. Instead, you buy a trip to Mars. But you better be on board with his Thai sub idea, otherwise he might get a little vicious with you.
Someone said you're just launched into space, no ship.
No, we'll just duct tape you to the nose cone of a rocket.
Only 20.
Oh,
it's only going to cost you $250,000. You're fine
up there. Oh, you should have said so. That's an add-on. That's an add-on.
That's an add-on. That doesn't come on the original contract.
That's one of those DLC for the.
So Space Force might bring the prices down. I believe there is a kappa in that, bud.
Space Force will make everything more expensive.
Yes. So someone says, when we use a large telescope to look at a specific spot in the sky, I'm going to just say maybe like Hubble, is it programmed to rotate as the Earth rotates?
Yeah, that's a really good question. So most telescopes, yes. If it's a space telescope, then you don't need to. You just point it and it just hangs out because it's in space. If it's on the Earth, then yeah, astronomy is still mostly a nighttime activity. They have to wait for clouds to get out of the way. They have to wait for good seeing conditions, and they'll pick a spot and they'll follow it over the course of a night if they need to do that very long kind of staring. Other kinds of instruments just stare at one spot at the sky and let the sky roll over it. And they're kind of always in like a continuous operation mode. But most telescopes will scan with the sky and account for the rotation of the Earth. Absolutely.
Yeah. Let's see. So, and actually, Leo, I just answered that, but he can potentially answer that too. Have you heard the whole thing that people are saying that the pillars of creation are gone? Have you heard that?
Yeah, we think that. So you look at the pillars of creation, this big nebula, and then you look at the stars, the first generation of stars that were born in that nebula, and they're big, they're bright, they're bound to go supernova any day now. And based on their characteristics and their variability, we suspect they may have already gone supernova.
Right.
And that over the next 100,000 years or whatever, we'll see the pillars of creation slowly evaporate.
Yeah, but they're still there, guys, right now, and we don't have any supernovae activity right now.
Yeah. It depends on what you mean by now.
Right. Well, you have that whole thing of being light years away, because our now is different than the now there.
Yes.
So, it gets
like, just watch that sequence of Spaceballs and you'll and pretend it's a picture of a nebula, and that's it.
Yeah, kind of like Betelgeuse. Yeah, exactly.
Yes.
Exactly. So that's 643 light years
Can
away.
we agree on a pronunciation of Betelgeuse?
Should we say Betelgeuse? What do you say? It's not Betelgeuse.
I'm pretty sure I say something different every time the word
I
comes
think
out
I
of my
do
mouth.
too. And then I hear other astronomers saying it. I think I go between Betel and Betel.
Betelgeuse.
Or is it Betelgeuse?
I like Betelgeuse.
Betelgeuse?
It's probably Battlegoose.
Battlegoose sounds amazing.
Ash and Fang. Battlegoose.
A supermassive black hole at the center of our galaxy. We're all going to die. Nope.
I mean, we are all going to die.
That's okay. So the latter part of that is true, but not necessarily.
This is two true but disconnected statements.
There you go.
There is a supermassive black hole at the center of our galaxy.
Yes.
Period. We're all going to die. Period.
There you go. That's amazing. Is that an actor? He's a science communicator.
And also actor. I do have an invitation to join SAG. Thank you very much.
Do you really?
Oh, my lines were cut. So you know that UFO trailer that I showed you, that I sent you the link last week?
Yeah.
With Gillian Anderson.
Right, because you were, yeah. Mm-hmm.
So I'm in it.
Right.
I have a speaking role. Like, it's not cameo. It was a legit speaking role. I had to audition and everything.
You say affirmative.
I say the tachyons are no.
The files are in the computer.
It's 2 lines where I'm being sassy with David Strathairn, and he gets mad at me, and it's awesome. But the director just told me that they had to cut my scene, or like the part of the scene where I spoke. He said it had nothing to do with my performance. He was lying, but it's all right.
Right.
But it was just, the scene just wasn't flowing. It just needed to be snappier. So they cut my lines. He said, but you're still in the movie, and you're still communicating with David with your eyes.
Oh, great. So you got like maybe even a nod?
Like a nod, or like I look a little bit ashamed, or probably just still sassy.
Sassy Paul with his silky voice.
But because I had a speaking role in a union film, I got paid union scale, and I got the invitation to join SAG-AFTRA.
Amazing.
Yeah. So I am an actor. Take that.
Let's take that, guys. Would the black hole eventually consume our whole system? Eventually, though, it depends on what you're calling system, and I'll let you answer that.
Over significantly long time scales.
Billions?
Say
trillions?
10 to 100 years, where we don't even have Greek prefixes anymore.
Wait, that we get consumed by the supermassive black hole?
That all things in the galaxy either end up falling into this supermassive black hole or get scattered away to infinity.
So how many years do we got?
Like, not flowing prose, not 10 to 100 as in a range of 10 to 100 years, but 10 to the exponent 100 years. So a 10 followed by 100 zeros.
There you go.
Sorry, I recognize that's a little bit unclear.
Yeah, I don't know if you did did you? Maybe you did 10 to 100, but the 10 to the 10 to the 100. You just trolled my chat.
Sorry.
They just got so scared. Everybody's like, we gonna die.
Well, you are gonna die.
It's true. Again, we've already broke down that statement.
But just unrelated.
Right.
Unrelated.
Right.
It's going to be heart disease.
Our star's going to die before this would even happen, guys.
Mm-hmm. Oh, yeah. Our star will die. The planet Earth will still be around, but it's looking dicey if we're going to be consumed by the red giant star when it goes.
Mm-hmm.
But there's a good chance it'll still be around, wandering the galaxy, and it might end up falling into a black hole, or it will get scattered away. And because of the accelerated expansion of the universe, each object in the universe gets yanked away from each other object, and it effectively becomes isolated in its own little pocket of existence.
Yeah. And so it could get consumed by the sun, or it could not, and then it could actually move, right? Its own orbit. It could pull back a little bit.
Oh, yeah. Our orbit will shift. Once our sun goes into the red giant phase, our solar system will be rearranged, reconfigured, given a fresh coat of paint. The icy moons of the outer worlds might melt. The innermost worlds, Mercury and Venus, are goners. Earth is a little bit icy. Mars is going to get warmer. It's going to be a whole new ballgame.
Someone said, is it the same nothingness outside our universe as within between galaxies?
Are you ready to have your mind blown?
I think everybody in here is ready because they only got 10 to 100 years.
Okay, they're working on that. Our universe has no outside.
We don't have a front yard.
Or a backyard. There's no yard to the universe. Our universe has no outside. We do live in an expanding universe, but it's not expanding into anything.
So what is space?
So space is stuff. Space is space-time. It's the coordinate system. There's vacuum. There's particles, all sorts of good stuff. So there's stuff in between galaxies, but there's nothing outside the universe.
Oh, man. So
not even nothing. As in, you might be tempted to call a vacuum nothing. That's still something. That's a vacuum.
Right.
There is no such, how about this? There's no such thing as an outside to the universe. Sit on that.
I'm gonna chew on that one for a bit. Wait, let's see. There was another. Theoretically, could we survive without the sun? UV lights everywhere and nuclear power.
Some of us might survive without the sun. There's this thing called plants.
Oh, right.
That
Photosynthesis.
really enjoy sunlight.
That's right.
And that's kind of the basis for food.
Yeah.
And so all higher forms of food, like
and
cheese,
oxygen, though, too, right?
I mean, I think oxygen will still be good.
Oh, really? Without plants?
Oh, yeah, without plants.
Yeah, they
Suck,
kind of help with that whole process.
So we might go for a while, maybe like 100,000 years until we deplete the oxygen supply in the atmosphere. I didn't think of that. Yeah, that'll suck.
Mm-hmm.
And yeah, so the inside of the earth is very warm, so we could dig holes and stay warm. And the earth will stay warm for billions of years, so that's not a problem. The surface will be very cold, which will be a problem. Need a lot of UV lights, geothermal energy, nuclear power. So I don't know, there's going to be like 60, 70 people. Tops.
Yeah, and so someone's like, man, skip my question twice. FFS. I got you. Okay.
Fast forward, Susan.
Susan. I'm never gonna live that one down. Does time stop? I'm sorry, I'm trying to not cough. I'm trying to mute me when I cough. Does time stop? And actually, I already know the answer, but I'll let you go through this. Does time stop at the event horizon of a black hole?
No, it doesn't. No, it doesn't.
Why?
Because who said it should?
Well, what if I'm looking at you and you're looking at me?
Aha. If you were to fall into a black hole.
Okay, so you're sending me in again. This is out.
Here we go again.
Now. This is twice now.
You know what?
Can you go in one time?
I'll do it.
Thank you.
Okay.
I appreciate that.
I fall into a black hole.
Okay, I'm eating Doritos on my spaceship.
Nice.
Cool Ranch.
I was going to ask.
Yeah, got
That's exactly what I was about to ask.
Okay.
I want to verify that.
All right.
And do I get to bring some with me?
I mean, sure.
I'm getting me a snack because I'm going to be in there for a while.
We compromise that you're going to go in, so I can send you with 2 mini bags.
Okay, like the little snack.
Yeah, the snack size.
These guys?
Right.
Perfect.
Okay.
That's all I need.
Good.
And yeah, because then they get on your fingers. And
right. And yeah.
So I fall into a black hole. And I die. And it's a finite amount of time. I can have a watch attached to my wrist.
Mm-hmm.
And I'll reach the event horizon. I'll fall through the event horizon. I'll reach the singularity in a given amount of time. And I can even predict outside the black hole how long it would take me to die to reach the singularity. If I'm dropped from a certain distance with a certain speed and all that, it's just math. It's just gravity. And I can attach numbers, say, okay, I'm going to die in 7.5 seconds. And I'll look at my watch, and 7.5 seconds later, I'm dead.
Okay. But me.
You eating the family bag, family size of the Cool Ranch.
Yeah, I'm not going anywhere.
You don't get to see me die. You don't get to see me actually enter the black hole. We have split views of what happens at the surface of the black hole. I just passed through just fine. No biggie. I may not even notice that I passed through the event horizon. It may be totally unviolent and peaceful. But you watch me approach the event horizon, but never actually cross it. The image of me chomping on the Cool Ranch Doritos gets slower and slower and slower and more redshifted. It doesn't totally freeze. It doesn't freeze 100%. There's a word here. Can I throw out a math jargon word?
Oh my God,
for
please.
Everyone?
Yeah.
We'll define it. The word is asymptote. Which is not a Norwegian curse word. It's a math word, asymptote, where you approach a value without ever actually reaching that value. You get infinitesimally close to that value, that number, without ever actually reaching it. So from your view, I will slow down and I'll get slower and slower and slower, but I'll never quite stop. It will take an infinite amount of time for me to actually stop.
Right, but I'll get bored watching you because it will be so slow to me that, to me, for all intents and purposes, even though you're not fully freezing, it will kind of appear that way because I don't want to sit there and eat my Doritos and not see any progress
once
with you
you finish
in.
that bag.
Yeah.
And it's only 2:30 in the afternoon, you're questioning your life choices.
Right.
Then you might just turn around and give up.
Yeah. And so what do you see looking back at me as you're getting closer?
So as I'm falling in, you get sped up. You also don't get sped up to infinity. You get very, very sped up, but not incredibly so. My view becomes incredibly distorted because of the extreme gravity. It's taking light from directions that I don't normally see and bending them into the path where I can see. So my vision is getting faster, or my view of the outside universe is getting faster. It's getting bluer. It's getting squished into a cone. And then actually, as I pass the event horizon, because of the extreme gravity, the light gets bent down into kind of like a hula hoop shape around me. So I see a ring around me. You get some very, very weird, distorted vision. And then I die.
And then you die. And then you die.
From the supermassive black hole. The one instance where I can connect those two statements.
Yes. Someone says, would it be possible to know what has fallen into a black hole by looking at its surface?
This is a huge question in theoretical physics. All the stuff that fell into a black hole contains a lot of information. Particle state, spin, velocity, like just raw information. Where does that information go? Does the information actually go through the event horizon? Does the information get pasted on the surface and then leaked out later? Does the information get pasted on the surface and then scrambled so that's totally unrecognizable? Huge question. You should ask Stephen Hawking, but you can't.
Nope. About nothingness outside, quote unquote, the universe. What's with the possible, quote unquote, other universe, multiverse, whatever, something? How are they connected?
Ooh, yeah. Because I got to be careful about the word universe here. So universe can mean a few different things, because you might hear that say the universe is 90 billion light years across. And then you might also hear things about, say, the multiverse. And then here I am saying there's no such thing as an outside to the universe. When I say universe, I mean the whole thing. the whole shebang.
Mm-hmm.
Sometimes when I say the universe is 90 billion light years across, I mean our observable patch of the universe. We can't see all the universe.
Right.
Some of it is just too far away for us to see. So there's more stuff out there that we can't see and will never see. So outside of our observable bubble is just more stars and galaxies and exciting flavors of Doritos. We just can't see it. Outside of that, there is no such thing as an outside. When you take the whole entire universe, however big it is, there's no such thing as an outside to that. There are various conceptions in string theory and inflation theory about something called the multiverse, where in addition to having our little observable patch of the universe and having our big whole thing to the universe, that in a very, very far distant, how should I say this? There are other bubbles of universes that have different physical laws, potentially have different arrangements of matter and energy. They operate totally independently of each other. They are separated from each other by space, by vacuum. There is stuff between them, empty stuff, but stuff. And then you call that whole package the multiverse. And then there is no such thing as an outside to the multiverse.
And multiverse is a concept, right? We've not been able to prove this, right?
Multiverse is a concept that is suggested by some advanced speculative ideas in theoretical physics.
Mm-hmm.
It is by far from proven. We've looked actually, because we wondered maybe an adjacent universe intersected our universe a long time ago before we got expanded away from each other. So we've looked in the cosmic microwave background if there's any, say, matching circles that would indicate our universe is rubbing up against another universe. All those searches have come up nil. There you are.
And someone says, why, and I know the answer, but I want you to answer this. So why does something like time get affected by a black hole like that? What causes it to happen?
Right. So what we learned in special relativity, Einstein's theory of special relativity, that space and time are connected and that moving clocks run slow. If you start moving, your clock runs slower relative to everybody else's. Gravity causes acceleration. Actually, gravity is acceleration. Moving clocks run slow. Here's the big jump. Accelerating clocks run slow. See where I'm going? With me so far?
Oh, yeah.
Okay. Moving clocks run slow. Accelerating clocks run slow. Gravitating clocks run slow. A strong gravitational field produces a strong acceleration. And even though you're not moving, it still counts. The act of acceleration itself causes time to run slower. So as you approach a black hole, you are approaching a source of strong gravity, and your clock will run slower relative to everybody else.
Okay. I think this is Chico. I was just going to type out the answer. What about the idea that what caused the Big Bang was a collision of these brains from the multiverse? Yeah, so you're going with string theory. String theory has not been holding up, though, for quite some time.
String theory is in a rough spot.
Yeah.
String theory is in a rough spot. String theory depends on some other speculative ideas in physics to be right. And a bunch of those speculative ideas in physics have been ruled out by the operation of the Large Hadron Collider. And so, yeah, don't know exactly where to go from there.
This is actually a really good question. What would happen if you keep going in one
Unlike all the others.
I know. I know. But this one, I don't think this one's ever been asked. What would happen if you keep going in one direction forever? Would you reach an edge? And I think he means in terms of the universe.
Right. There is a better question. Yes, this is a Marriott. Good.
Great.
Guess.
Great.
Okay, so let's take away the expansion of the universe, because the edge of our observable universe is expanding faster than the speed of light, so you'll never catch the edge. Let's say the universe is static. It's not expanding or contracting. It stays fixed, and you were to travel in one direction. What would happen? Well, if we live in an infinite universe, then we live in an infinite universe and you just keep going. It could be that our universe is what's called closed, which means one or more dimensions wrap back on themselves, which means if you go in one direction, you will end up where you started. And by all accounts, as far as we can measure, there is no curvature to our universe. So it's not like the surface of the earth or the surface of a beach ball or the surface of a horse saddle. There's no curvature at all to our universe. It's totally flat, but there are flat geometric structures that do have closed dimensions. So I think I brought this up before one day. The surface of a cylinder is flat. It's geometrically flat. So you can still have a flat universe. There are, in fact, 17 possible geometric configurations, 17 topological configurations for a flat space-time universe. And we've looked to see if our universe is closed, if it wraps in on itself, looking for mirror images, patterns of galaxies. There's some statistics games you can play. Haven't seen anything. So that suggests either our universe is infinite, or if it is closed like this, it's closed on scales bigger than our observable bubble.
Have there been any new discoveries regarding dimensions? Is that even being researched that much? As I imagine, it's pure theoretical mathematics.
We're wondering about, like, we have our 3 spatial dimensions and our 1 dimension at a time. It's a natural question. There are 2 natural questions that come out of this. One question is, are there any more? And the other natural question is, why 3 is space and 1 at a time? What's causing that?
Right.
We have no answer to what's causing why our universe picked 3 spatial dimensions and 1 dimension at a time. There are some, again, speculative ideas about gravity, the nature of gravity. One of the very puzzling things about gravity is that it's so incredibly weak. It is trillions upon trillions of times weaker than any other force.
Yeah, it's the weakest of the 4.
It really stands out. It's just the runt of the litter when it comes to the forces. And we don't understand why. One speculative idea is that there are more spatial dimensions to our universe that we simply don't operate in, so we don't care ever. And that gravity is the only force that operates in all of those dimensions. And sometimes it leaks through to our 3 spatial dimensions. And that's why it's so weak, because it's really diluted over many more dimensions. But then you start asking, well, why is gravity special in this way? Why don't any of the other forces connect to the other dimensions? And they say, don't ask too many questions.
Don't ask too many questions. So if you go back in time, there'll be nothing because everything moves forward in time?
Sure.
Yeah, I mean, that's a tough one because, I mean, time is
slippery. As far as we know, it's impossible to go back in time. It appears that everything marches forward in time. We don't fully understand why. It just appears so. We don't have any physical theory or physical model or explanation or mathematical equation that we can point to and say, yeah, everything moves forward in time because this. We don't have that. And as you go back in time, at a certain point, 13.77 billion years ago, our entire universe is in the singularity of the Big Bang, which means we really don't understand it.
Yep. And time is really, really wonky.
Wibbly wobbly. I've
Right.
heard some very erudite people say.
And Chico, we can talk about the nature of gravity and how it interacts with it. We can talk about the fundamental forces.
We'll do it, yeah.
Yeah, we can talk about that
all day long.
Yep, but we are. Let's see. So, where is the start of a cycle path you are walking? Of a circle path you are walking. Where is the start of a circle path you're walking? I don't know if that's rhetorical.
I believe it is.
Okay.
In jest.
Okay, got it.
My good fellow.
Can we manipulate gravity with another field?
We can manipulate gravity. For example, the more food I eat, the stronger my gravitational field becomes.
And is that because you gain mass?
Exactly. Mass and energy cause the acceleration effect known as gravity.
And is there an equation for that?
There are several equations for that. Many glorious mathematical equations known as Einstein's general theory of relativity. 10 equations. 10 of them. One for each finger. And these 10 equations are ridiculously complicated, but they're really fun. And these 10 equations tell us the relationship between the bending and warping of space-time, which is what we call gravity, and the contents in that space-time, the mass, the energy, the stress, the twisting flows, the way the matter moves and behaves is encapsulated on one side, and then the other side encapsulates space-time's response to that.
And so Ghost, he was asking this earlier, but the question that he asked would just lead to annihilation. So what do you know about antimatter?
What do I know about antimatter? Antimatter is, if you take a particle, electron, a quark, neutrino, whatever, just a particle, keep its mass, keep its spin, keep everything the same except its charge, and flip that charge to the opposite side, you have created an antiparticle. And this antiparticle behaves exactly the same as its partner, except with the opposite charge. So if you put an electron in a magnetic field, it might go this way. If you put its antimatter particle called the positron in a magnetic field, it will go this way. It'll be complete opposite, totally symmetric. Antimatter is not normally found in our universe. Our universe is dominated by our kind of matter, which is good because when matter and antimatter touch, they annihilate each other into pure energy. So if there's a lot of antimatter floating around, there would be a lot of, deathly explosions. Why our universe has more matter than antimatter is an unsolved mystery in modern physics.
Yeah, because it should have annihilated, right? We got leftover matter.
Because when you start cranking up machines that generate matter, it always comes with antimatter. They are produced symmetrically. So if you have a machine that turns out 10 pounds of electrons, it's also going to turn out 10 pounds of positrons. The fundamental interactions of physics that generate matter, generate antimatter in equal amounts, this balance must have been broken in the early universe.
And let's see, there was another good question. Where was it? If time gets slower when approaching a black hole because of gravity, is there something like time going faster because of gravity? Let's see. There was another one. So that was antimatter, and how close are we to a theory of everything?
No closer than we've ever been. We really thought string theory was something promising, especially when it first got going in the 70s and 80s, and new structures in the mathematics were found, and new connections and new symmetries. And it seemed like, pretty exciting, and then it went nowhere. And in the late 1990s, there were some very interesting things with developments with what's called holographic theory and some strange correspondence between various structures used in string theory and various other structures used in field theory. That went nowhere. And yeah, I mean, honestly, physics is in this really weird spot where every day that goes by with the Large Hadron Collider not finding anything interesting, we start looking around, and like all our best guesses for approaching, even getting us on the path to a theory of everything, look more and more, or I should say less and less plausible, less and less tenable, less and less workable, and kind of don't know where to go because we've invested a lot in string theory.
And so Ghost said matter X antimatter equals Big Bang is, I don't.
Right. So matter and antimatter coming together equal big explosion. The Big Bang was not an explosion, though.
What was it then?
It was an expansion of space. We still live in the Big Bang. The Big Bang is still happening now. The Big Bang is just the expansion of the universe. It's the term we give to the history of the universe, especially the early universe. It was not an explosion in space. It was and continues to be an explosion, an expansion of space. The universe did not arise in some point in space. It arose in a point in time. It is a point that everybody in the universe can point to in their past 13.77 billion years ago.
So someone says maybe the missing antimatter is just hidden beyond our current notice.
Yeah, so we wondered that. We were pretty sure that outside of our observable bubble of the universe, our observable patch is just more universe. It's not like an antimatter universe is right around the corner, because the fundamental mathematics that go into cosmology and describe how our universe work say that at large scales, everything's pretty much the same. And this is borne out by observations. And you might wonder, like, if you look at a distant galaxy, maybe you're looking at an antimatter galaxy with antiprotons and antineutrons, like everything's anti. But then galaxies don't live in isolation. They merge with each other. There's gas flows falling in. There are gas fountains flowing out. It should be blowing up constantly, which we would, probably notice.
Right. And so is the theory of everything, and this metamorphosis asks this, is the theory of everything the ultimate goal in physics, or is it a tool to help us understand everything better? I like that.
That is a good question.
I like
that. So
that.
It's not like, that's a really good question. Not every physicist is concerned about trying to figure out a theory of everything. In fact, the majority of physicists are not on some quest to understand a theory of everything. It's only a small minority, a very small minority of physicists are trying to unify the forces. Most physicists are trying to solve other problems because there are a lot of things we don't understand about the universe. And so they pick some particular discipline, some particular field, some particular open question that we're still investigating and pursue that. And have happy, healthy careers, as happy and healthy as you can be as an academic. And, and they're happy and they write papers and they get prizes and awards and then they retire and they are remembered for their great contributions to science without ever even approaching the problem of the theory of everything.
And since we're getting low on time, but you could probably, this is a good question.
I can go longer.
You can? Cool.
Yeah.
So then
the maids came, so I got fresh towels.
So how long do you have? Do you have like another conditioner? What do you have? How much time do you have extra?
Let's go, I don't know, 15.
Okay, cool.
I should get back to the conference at some point.
Yeah.
I'm playing hooky.
You're kind of doing side science. Let's see. So is the theory...
This is my side science.
Yeah.
Don't tell my main science.
Is the theory... Wait. That's something we already asked. So it's called annihilation. Yes. And then... Oh, yeah. This is a good question. I really like this one.
Oh, annihilation is a good candidate to break up, to do that trick. where you break up a word and put a pause in and make it sound more dramatic. Annihilation.
Elation. I'm not
okay,
feeling
maybe not.
that.
I was wrong.
Yeah,
I was wrong.
No, I didn't.
Didn't work
I didn't
out.
feel like that.
The H threw me. I didn't know how to treat it.
Do you have your own ideas or theories that expand on or go beyond the academic ones?
Yeah, I got nothing.
I
remember last season of How the Universe Works with Science Channel. They're asking me like, do we know what's inside a black hole and what is the nature of the singularity? And I said, yeah, we don't know, and I'm not smart enough to tell you. And I remember when they aired that bit of the segment, but they cut off right before I start to say, and I'm not smart enough to tell you. And but you can see me grinning, like starting to grin because I just came up with the joke.
Mm-hmm.
And so you see me talk and then start to go like, and then they cut.
Oh man, not fair. Let's see. So I know we use interferometers in astronomy. So a good example of one would be LIGO. That's the laser.
Or
meerkats. In astronomy, I was wondering if there are naturally occurring interference patterns of stellar light we see.
That's a really good question. I honestly don't know. I'm thinking no. You have to be very, very careful to deliberately set up, and obviously light, well, let me say this. Obviously light interferes with itself all the time, but to do so in a way that you can leverage for astronomical gain, you have to devise a specially prepared setup.
Yeah. And Joe had a question. He says, if antimatter doesn't exist in our universe, does that mean it's a myth?
So antimatter doesn't appear in abundance. I should have been more careful when I said that. It's certainly not 50-50 with normal matter, but high energy reactions do still produce antimatter. We can make it in the lab. We see it as byproducts during supernova explosions or quasar outbursts. We see positrons. We see the antiparticle flows, and they do collide with normal matter, and then they blow up.
So it does exist.
And they blow.
It can exist,
but not in abundance.
Right? Not a lot. So can I ask Mr. Paul, Dr. Paul,
Mr. Dr.
Paul, about the multiverse theory and if galaxies would interact with each other in a multiverse?
So our galaxies in our universe, our observable patch, certainly interact with each other. Galaxies collide. We're on a collision course with Andromeda right now. You just have to wait 5 billion years for the fireworks to start.
Yep.
Outside of our observable patch, whether there's just more universe or there are multiverses or anything, we will never interact with it. We will never see it. They will never see us. We are outside of any possible future contact with anything outside of our observable patch. Straight up. As even if our universe is far larger and far more complex, and we discover some way to unlock it, and we verify these like ideas that appear in inflation or string theory, they are forever removed from us. That we can't communicate with them, we can't talk with them, we can't touch them, we can't tell them how much we miss them. They're just gone forever. We are effectively alone.
And someone asked about, and this was a while ago, but they asked about, I don't know who it was. Maybe you guys can, someone, whoever asked this, if you're still here, you can ask it again. Something about type 1 civilization. But he did even say, is he even okay with talking about that? But I mean, those questions happen.
And I don't know, the Kardashev scale type thing, like the type 1, you can harness the energy of a planet, I think, or I forget the scale. Type 2 is you harness all the energy output of a star and do cool space laser battles with it. Doesn't specify what you do with all that energy. Type 3 used all the energy in a galaxy. Okay. Like, I don't see the point.
I don't either. If not, even light can escape a black hole, then how come you see light and matter pour out from black holes? It's an accretion disk.
Yeah, exactly. So as stuff falls into a black hole, it can heat up, it can light up. We can see it. If it crosses the event horizon, if it crosses that boundary, then it's gone, straight gone. But material can find itself forming a disk around the black hole, an accretion disk, as it falls in. Those accretion disks have incredibly complicated physics with twisting and winding electric and magnetic fields that can whip particles around the surface of the black hole without reaching the event horizon and form jets that shoot off into space like tens of thousands of light years. This is all the environment around a black hole without actually falling into the black hole itself.
So it is still true then that nothing escapes the event horizon.
Right. If you cross the event horizon, you're a goner.
You're done.
You're just done.
Yep. So with the expansion, the interactable portion of the universe is getting smaller and smaller technically. Yes.
Mm-hmm. True.
As they drift out of our reach. Or
yes.
Or line of sight, I guess you could say.
Yeah, out of any possible physical contact. So there are actually galaxies right now that we can see that are receding away from us faster than the speed of light. The light they sent that's reaching us now, they sent a long time ago before they were going this fast. Now we know they're going that fast and we'll never be able to reach them. So our observable, even though this is a wonderful contradiction, these two statements, we live in an expanding universe.
Mm-hmm.
Because of that, our observable patch gets smaller and smaller.
Yeah. I think I'm going to need a link to that video that you did with Fraser. That's amazing, where you explained.
Oh, all the boundaries?
Like the Hubble bubble stuff. Yeah. Like with the observable and what we can see and how that's actually,
yes. The particle, or, the cosmological horizon, all that.
Yeah.
All those. Yes.
Yeah.
That was great video.
That was an amazing video.
Landmark.
Yes.
YouTube history.
Yes, I might need a link to that, so you could send that to me after, so we can watch that, because I think a lot of people would like to see that. Do you ever think we'll ever reach a limit of science?
I had a really, really fun conversation with Fraser when we were in Iceland. He recorded a something for something.
Mm-hmm.
And I'm sure it's online somewhere.
Uh-huh.
Where we talked about the limits of science. And science, in principle, there is no limit to our knowledge. I believe there is an infinite amount of things to learn about our universe, or at least so large that it's effectively infinite. But our ability to acquire that information, to collect the data, to synthesize it, to analyze it, to understand it, to wrap it within the context of previous scientific understanding and models and mathematical theories and everything, that becomes progressively harder. Science right now is a lot harder to do than science 100 years ago across all fields.
Mm-hmm.
We've learned the easy stuff. Now we're working on the hard bits that require tons of data, that require expensive machines, that require giant collaborations of 100 or more scientists spending 10 years to come up with a result. And what I worry about is that, no, there's no end to knowledge and learning and science, but it's becoming more and more difficult, and that science is not grinding to a halt, but like relatively grinding to a halt, where the same amount of effort gets less and less return. It's like diminishing returns.
Yeah, exactly.
I could have just said that.
You could have, I could
have made that really short.
Do we have enough knowledge to computer simulate black holes? Yes.
No, not quite.
No, Kip Thorne.
Kip Thorne.
Kip Thorne.
What about Kip Thorne?
Well, he got the mathematics.
And he has a beard and seems to know what he's talking about. And okay, just a black hole by itself with nothing interesting going on. Actually, we could just write down the mathematics. We don't need a computer to simulate that. We know exactly what's going on. You start adding stuff to it in the vicinity, like light or particles or Cool Ranch Doritos. Great sponsorship opportunity.
I know. I was about to say I should have contacted them. Okay.
And yeah, you know, they're people. You just email them. And once you start adding that, the physics becomes incredibly complicated, very, very fast. This is an open area of research where there are multiple groups around the world using high-powered computers to simulate the environments around black holes, especially merging black holes merging with neutron stars, the radiation properties, the gas properties, the role of electric and magnetic fields, that whole accretion disk thing, that story I told, you know, with the jets. We don't have a complete picture of that.
Right.
We don't have a full understanding of the physics of that. That is a very complicated, very juicy problem.
Yeah. Yeah. And someone goes, wait, faster than the speed of light? I thought you can't go faster than the speed of light. You can't.
Ha.
You're right. You can't.
You're wrong.
What?
You can go faster than the speed of light.
How?
Who tells you these things? Who tells you these things?
How do you go faster than the speed of light?
Where are you learning this?
Are you talking about tachyons?
No, of course I'm not talking about tachyons.
Because those don't exist.
Those aren't a thing.
Okay, so can you go faster than the speed of light?
By the way, I may have convinced,
we're
going to see next year, I may have convinced a certain sci-fi series to stop using the word tachyon and start using the word neutrino.
Oh, really? So can you go faster than the speed of light?
Yeah.
How?
Okay. Special relativity, which is where we get this whole speed of light limit thing. It is a law of local physics.
Okay.
It applies for stuff right in front of your face. Like if a rocket is blasting by you,
right,
you will never ever see it go faster than the speed of light.
Right.
But it's local physics. It only applies to your local area, your neighborhood. If you go out and look at the distant edge of the universe, special relativity does not apply. It's supplanted by a theory of relativity that is slightly more general than that, a general theory of relativity, if you will. And for things far away on the other side of the universe, they can have whatever speed they want. It doesn't matter.
Are you talking about the expansion?
I'm talking about the expansion of the universe. Another way of putting this is that speed, the word speed, only applies to local things. That something on the distant edge of the universe doesn't have a speed per se. Speed is something you can only measure locally.
Oh man, he just flipped this. So what is traveling faster than the speed of light?
So what was that?
What is traveling faster than the speed of light? I just asked you, but I'm just having you clarify.
A whole bunch of galaxies. Yeah. Most of the galaxies that we observe are expanding away from us faster than the speed of light.
So it's the expansion.
Well, the expansion rate is constant.
Right.
The expansion rate is relatively constant.
Relatively.
And it's constant at any one point in time. It changes with time, but at any one point in time, it's constant throughout the universe. It's the same number, which means that the farther away something is, the faster it recedes from us. And at a certain point, it's so far away, it's expanding faster than the speed of light.
Everybody's like, huh? You don't get it? What's local? What's local and what's not local?
Local is a mathematically defined term that it's not a fixed number. It is comes about in the equations, and special relativity tells you when you're not local anymore. Special relativity tells you when it doesn't apply anymore. It has to do with your current acceleration. It's a little bit nuanced.
So someone goes faster than the speed of light. Are you sure about that? Yeah. As far as the expansion goes.
Yeah, far away stuff. Really, really far away stuff. I'm not talking about like to the nearest Costco. I'm talking about galaxies on the opposite side of the universe. They can have whatever speed they want.
Mm-hmm.
Nobody cares.
And let's see. I only keep hearing...
That's a good question, Ashenfang.
Yeah.
Ashenfang.
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 Like our galaxy isn't going the speed of light unless we look at it from another galaxy.
Correct. All
that's
galaxies are receding. Yeah, all galaxies are receding from all other galaxies. And if you pick a particular point of view, then you, if you're sufficiently distant, we see a galaxy on the far edge of the universe, and it's receding away from us at the speed of light. If we're living in that galaxy and looking around, we'd see the Milky Way receding away from us at the speed of light.
And that's technically why there's really no center, because it's all a part of your frame of reference. You're going to always see you being the center of things, regardless of your positioning in our universe.
And to wrap this all the way back around, because there is no center, there is no such thing as an outside.
Wow. Mic drop on that.
Meditate on that.
Yeah. Well, thank you for giving us another 15 minutes of your time. We will let you go back to the conference. And yeah, guys, this is Dr. Paul. Please tell everybody about everything you do, because my brain.
Whew.
Please.
What do we do? Let's see. Thursdays, 4 p.m. Space Radio. It's a radio show where you call in. We broadcast on Twitch and YouTube, so you can ask questions there. Ask a Spaceman episode dropped today. I totally forget what the subject is. I think it's about dark energy. I think today is Dark Energy Day and how it causes the expansion of the universe to accelerate. I write articles for space.com. I have a book coming out this November called Your Place in the Universe. And I enjoy cheese. Common theme. I'm on social media. This Wednesday, I'll be in Manhattan for Siren Modern Dance's Summer Soiree, where we're talking about science, dance, and time, the nature of time. We're launching a new performance called TikTok, which is going to be very cool. This is the big party to announce the collaboration. We'll have a studio showing of it sometime in December, but this is the party to get things started.
Yeah. And I'm not leaving, but we're going to say goodbye to him.
But I am.
But he's leaving. And yeah, we'll see you next week.
Absolutely.
All right. Have a good one.
Thanks again for having me on, and tons of great questions. Loved
yes.
it.
All right. Bye-bye.
Bye.
And we just take this off. I really need it.